Here to talk to you today about mixed latency data pipelines. This talk was originally supposed to be by the CEO and founder of Twirl, Eric, but on his way from Stockholm to Austin, he stopped in New York to take a few meetings and he got the flu, so he couldn't be here. So I'm doing the talk instead. So thanks for having me. A little bit about me, as the introduction said, as Julian said, I started my career as a cowboy and I decided I wanted to use my brain a little bit more, and so I found my way to data science. And then over the course of 10 years, I worked my way sort of from data science to analytics to data engineering to software engineering. And now I run growth at a data platform startup. So a bit about Twirl. Twirl is a managed data platform. It's for teams and companies that either can't build a platform themselves or they don't want to. And it's born out of the insight from building data platforms at a variety of companies that the MDS is really nice, rest in peace MDS, but it's a really nice experience, a nice user experience, but it doesn't get you where you need to go typically when it comes to more mature data teams. And so some examples of that, some examples of the types of functionality that we found teams tend to need is the ability to mix languages in a very native way, so to use Python, to use SQL, but also to use arbitrary containers, Docker files, to run Java or C++ or whatever. And the ability to interoperate between object stores and data warehouses in a natural way. So you may have PDF files or videos or images or what have you, unstructured data in an object store like S3, but also structured data in a warehouse, and you need to be able to kind of mix and match between those in a natural way. And then the third one, which is relevant for this talk, is that you need to be able to mix latencies in a natural way. So oftentimes teams start off with a batch processing platform. It's usually fine at the beginning to run things once a day, and that's a very easy way of thinking about the world. But over time, there are opportunities that require lower latency. There's often someone who comes in and asks if a dashboard can be real time. But even outside of the analytics world, if you want to integrate data into a product and support data-powered product features, you need to be responsive. And so having lower latency capability is valuable out in the world. So I don't think anyone will disagree with this. Streaming is nice because it's super low latency, but it's also quite hard. It requires dedicated infrastructure, something like Flink or Kafka Streams or what have you. And it's typically not what teams reach for when they're first building out a data platform. It's usually an appendage. Batch is really nice. It's easy to think about, but it comes at the cost of higher latency. Your data doesn't arrive with the same freshness. And so as we set out to build sort of the data platform that we thought teams would want to use and that we would have wanted to buy if we could have in the past, we were tempted to think about how could you get to a place where you can offer low latency, but with the sort of semantics and the ease of use that people are used to from the batch world. And so the first thing to think about as we think about how to get there is that batch sort of has at least two flavors. The first is your sort of classic partition batch. This comes from the Hive world and Airflow, and I think Luigi supported working this way, where you take time and you have your data and you split it up into equally sized segments, maybe days, maybe hours, and you run your computation over each chunk of time. And this is really nice. It lets you be idempotent, so you can run the same code again and do the same processing, get the same result, and that's a really nice feature. But it can be hard, especially when you want to change the partition size. If you want to move from a daily partition to an hourly partition to every 5 minutes, if you try to move towards low latency, it can be really difficult to change that style of system and evolve it. On the other hand, there's what we call catch-up batch. It's sort of DBT style incremental materializations. And this is the idea that instead of segmenting time into equally sized chunks, you can check your asset, your table, whatever your target is. Say, how up to date is this? What's the water line? What's the last event time? And then you can process just those rows that you haven't processed yet, and you can catch up. And so we think that this style of batch processing can actually get you more towards low latency. You can easily change the cadence at which you run this from daily to hourly, and it should just work. There's some caveats, but it should allow you to get towards lower and lower latency. It'll never get you to streaming event by event, but it could get you to potentially 2 minutes or 5 minutes of latency, which is enough for a lot of real-world use cases. So Twirl's working on this. The goal for Twirl is to expose a data platform in a way that allows the user to not be exposed to concepts they don't need to, so keep it very, very simple, but then evolve with you and not require the addition of extra infrastructure as time wears on. So in particular, we're thinking about systems where you start with batch, you start to have opportunities to go more low latency, but you usually just table those opportunities because it's too much of an infrastructure investment. And we don't want that to happen to teams. We want you to be able to kind of naturally grow as your needs grow. So this is a DAG. And this is sort of the naive way you might approach going low latency with an incremental job. So you can take a DAG like this, you do a DAG run, a topological sort. You can notice that A and B are sort of the same level, so you can parallelize those in a thread and then run C after them, and you can set that on some kind of schedule every 5 minutes. And that will sort of work if you have small data that can process quickly, or if everything in your system is easily incrementalizable. But that's typically not the case. It's usually almost impossible to incrementalize everything in a large DAG. And it's also usually not desirable. It's extra work, and you often don't want things to be super low latency that don't need to be. It's a waste of compute, it's a waste of effort. So the solution is mixed latency. You run some parts of your data processing at one latency, hourly, daily, whatever, and another at another. So very commonly hourly and daily, but over time you tend to add more. So what that typically looks like in many data platforms, I'll pick on dbt for example, is you start to tag your nodes with how often they should run. So you might have a tag for each thing that should run hourly. You'll say it's an hourly job. You have a tag for everything that's daily. And then you'll have 2 cron jobs that are scheduled, and they're a dbt run for the tag of daily or hourly, and you schedule them appropriately. And this works pretty well. I've run this myself in production a few times. But you do start to have some challenges. So for example, this bottom node is purple, and that represents an analyst coming along and trying to add a new node to a graph. And the experience they have is they add a SQL model in dbt, for example. They add a tag of hourly, and they expect it to run hourly. That's sort of the expectation they have in their head. They don't expect to have to check anything else about the graph. But it may well not run hourly. It may well be scheduled in the hourly DAG, but have parents that are in the daily DAG, and therefore just waste compute 23 times a day, and once a day update. And the analyst will be confused. It's like, I tagged it hourly, why is it not hourly? And this problem gets much, much worse as you start to add a 4 times a day DAG, and an every 20 minutes DAG, and so on and so forth. It becomes really difficult to even predict the actual latency of a table when you add it into the DAG. So the solution, we think, it's not a completely novel idea, is to not do DAG runs, to remove the concept of a DAG run, and to think about running the node, and having the node know its state, the last time it ran, the last time its parents ran, and allow it to specify that it wants to run every time both its parents are updated, but not more than once per hour, for example. And to have these kinds of conditions where the node can say exactly how often it should be updated. So a very common problem, probably mentioned in this conference at least 10 times, is an analyst or an executive or someone noticing that a table is late, it's stale. The data isn't there where it should be. And the most typical reason for this is that there's a failure in a job, but it doesn't have to be the thing itself that failed, it could be upstream. And so in a typical DAG run system, you will have some failure and then it'll propagate. So you'll have skips further down your graph. And if you're the analyst that's responsible for the bottom node in this graph, you can go to whatever pane of glass you tend to look at. You can see that the run that contained your table is red. And you can look at the logs and say that, okay, there's an error and some skips, and that's probably what's causing my table to be late, and you can suss that out and try to fix it. If there are a lot of errors and a lot of skips and they're not all connected, it can be a little bit difficult, but in general, it's not such a big problem. In contrast to that, when you start to schedule things with different latencies, so for here, for example, imagine the blue DAG is daily and the rest of it is hourly. Excuse me. The issue that you run into is that the DAG that contains the failure is not always the DAG that runs the table. So the analyst is going to the hourly table, the hourly DAG, because that's where their table is, and they're saying everything looks green, everything is fine, but my table is still stale, because it has a dotted line, it has an input that isn't scheduled at the same time, and that other scheduled run failed. And that can be really annoying and really hard to figure out, especially if you have many of these. So in a system where every node runs itself, this is still a problem, because now you don't even have a DAG run where you can go and check the logs and say, okay, here's what's happened, here's what's failed, and that's probably caused the skips or the staleness that I see. And so if you're going to run a system like this, it becomes very, very important to add tools that allow you to say, okay, my node's not running, its conditions for running aren't met, a parent is stale, a parent hasn't updated, and you need to provide introspection tools. And so we've put a lot of work into that sort of thing. The last thing I want to talk about is partition consistency and consistency. So that's the idea, sort of analogous to a transactional consistency, is that sometimes when you're analyzing data, you want it to be at the same freshness horizon. So an example of that might be, imagine you have a simple system where you have transactions flowing in and they update every 5 minutes, and you also have some sort of ETL job to give you user information that happens every hour. When you join those two data sets, when B first updates, everything is sort of fresh because 5 goes into 60 evenly. But over time, A will continue to update, and a table that reads from both might be looking at a new version of A, but an old version of B. And the result is you might have transactions that don't have a user attached to them. They're orphans. And you can sort of work around this in a SQL context pretty easily with a left join. It's the standard way you do it. You'd say, okay, here's the data I know exists that I care about, and I'll join in the transactions that actually have a user. But as you try to incrementalize that, that can be really difficult. And if you leave the warehouse context and you're doing your processing in a container, for example, you don't have the same options. So this is a case where an orchestrator that's data aware can actually solve this for you, and it can sort of do a reverse incrementalization where it says, okay, when I update C, I'm only going to give it data that was available at the same time as when B updated. And so at Twirl, it doesn't stop there. We're working on, we think this kind of abstraction of a data-aware orchestrator can extend to even actual real time. So there's not really any reason why a node in this graph couldn't have a buffer and actually do receive events and do joins and aggregations and things like that. And there's no reason why a node couldn't have a connection to the internet and receive HTTP calls and have a cache and serve data in a real-time fashion, which would make it much more viable to serve machine learning results directly out of your sort of orchestration platform and have everything all in one place. And that's all the material I've got. Thank you for your time and attention.